There are two kinds of energy that are of primary importance when we're dealing with mechanics. Kinetic we talked about the other day. The other kind is potential energy. And this is energy that's stored. You can kind of think of it as energy of position, in a manner of speaking. Kinetic energy is energy of motion. Potential energy is energy of position. And there are two types of potential energy we're going to deal with for the moment. The first one is spring potential energy. When you have an object on a spring, if you stretch or if you compress or stretch the spring, and then you let it go, this object will then gain kinetic energy. So there's this energy that's stored up as you stretch it or compress it, and that is the spring potential energy. Now we know that work, in its most basic definition, is F cos theta times d. In this case, that just becomes force times our delta x, because we're moving an object. For compressing or stretching the spring, we're moving an object, and we're applying force in the same direction or the opposite direction as the object is moving. Okay, so the work you do to compress a spring is equal to the displacement times the average force. Okay, and we know that spring force is kx, or minus k delta x, sorry. So the spring force increases linearly, and at equilibrium we have zero spring force, and then when we get to a position when we get to some delta x, then the force is k delta x. So the spring force, the initial spring force is 0, the final spring force is k delta x, and it increases linearly, so this average force is then 1/2 k delta x. So the work is half k delta x times delta x. So you do 1/2 k delta x squared work in order to compress the spring, thereby giving the object this much potential energy. And this is the definition of spring potential energy. Potential energy of the spring is 1/2 k times delta x squared. You get positive potential energy whether you stretch or compress the spring, because either way it has energy that's being stored that can then turn into kinetic if you let go. That's spring potential energy. We also have gravitational potential energy. And we know that to lift an object from here up to here, in order to move it up there, you have to exert a force equal and opposite to its weight. So the force you apply is mg. The amount of work you do is positive when you go up, negative when you go down. So for a positive moving up, our work that you do is mg delta y, force times distance. And this is the definition. So if you do that much work on it, you give it that much gravitational potential energy, mg delta y. So gravitational potential energy is mg delta y. Spring potential energy is 1/2 k delta x squared. So those are the definitions of our two potential energies. Now let's see where those come out in our equations. We worked out the work kinetic energy theorem says that the net work done is equal to a change in kinetic energy, delta KE, which is 1/2 mv final squared minus 1/2 mv naught squared. Okay, but if we split this up into work done by conservative forces and work done by non-conservative forces, and these work done by conservative forces, all the work done by conservative forces is stored as potential energy. Gravity is a conservative force, it gives this potential energy. Spring force is a conservative force, it gives this potential energy. The non-conservative forces don't conserve the energy of the object. That work doesn't necessarily remain with the object. It's often dissipated as heat or or something else like sound or something. So this work done by conservative forces, for example, if we, right now the only conservative forces we know about are gravity and spring force. So the work done by non-conservative forces plus work done by conservative forces, if I move an object upward, then gravity will do, the work done by gravity will be negative because gravitational force is down while I'm moving the object up, negative mg delta y. So that gives us minus mg delta y. Likewise, the work done by the spring force is pushing against where I'm moving the object as I stretch or compress the spring. So the work done by the spring is minus 1/2 k delta x squared. So now I would have a minus 1/2 k delta x squared. The reason that we define potential energy as the positive is now if we look at this, we can rearrange this and say the work done by non-conservative forces is 1/2 mv final squared minus 1/2 mv naught squared plus mg delta y plus 1/2 k delta x squared. So we have work done by non-conservative forces is a change in kinetic energy plus this should be a change in, these are all changes in gravitational potential energy, plus a delta PE gravitational plus a delta PE spring. And later on we'll find out that there's a potential energy from electric force, and that would go over here as well. So in general, the work done by non-conservative forces, like friction or air resistance or any kind of pushing force, is equal to a change in kinetic energy plus a change in potential energy. And together, this K kinetic plus potential energy is called mechanical energy. So in simplest form, we can say that work non-conservative is equal to a change in mechanical energy, right? So non-conservative forces, we talked about them conserving energy of the object while we were talking about the mechanical energy of the object. Conservative forces conserve the mechanical energy of the object. Non-conservative forces do not conserve the mechanical energy of the object, right? And this is a way we're going to use to solve a lot of problems. Now, if we have a scenario where there are no non-conservative forces acting, if no non-conservative forces are acting, then work done by non-conservative forces is 0. So the change in mechanical energy is 0, which means that change in kinetic plus change in potential is 0, which means that the kinetic and potential, the changes in kinetic and potential energy are equal and opposite, meaning energy is just going back and forth between kinetic and potential. As a concept example, consider a pendulum, which is just like a string with a mass on the end that swings back and forth. So it's up here, and then it goes down to here, and then goes up to over here, and then back and forth and back and forth. It's just swinging along. The only force acting on this, the only force that's doing work is gravity. Tension is always pulling toward the center of the circle, which is perpendicular to the displacement. So gravity is the only force doing work. So we just are swinging back and forth between kinetic and potential. Up here, we're the highest, so we have a maximum potential energy, and our kinetic is 0 up at the top here because it stops for a split second. Down here, our KE is at a max, and our potential energy is at a min. And over here, our KE is again at a max, and our potential energy is at a minimum. Our KE is at 0, and our potential energy is at a maximum. Notice I said the potential energy is at the minimum. You'll notice in all these equations, it's always a delta PE that shows up. The So it's important to note that the zero of potential energy is arbitrary, because all that ever matters physically is a change in potential energy. So generally, whatever the lowest point is in a problem, we could call this P equal, we could say this lowest point of the pendulum is zero potential energy. That would be most convenient. So, but we could also say that the zero is down here or up here or whatever. It doesn't actually matter. Just like what was the zero, like when we did kinematics, where we said x equals 0 didn't matter. What was important was that delta x. It's the same here. You can set your potential energy to 0 wherever you want to, but setting it intelligently will often make your problems easier to solve.